All right, everyone. Just like they said in High School Musical 3, the boys are back. And this time we are back with the Verilog Workshop, the third workshop of the winter quarter. I hope you are all here and ready to learn a little bit about my favorite programming language. But first, we have a few important announcements. The first one being, please sign in at this link. You know the drill, it's in the chat, helps us a lot, makes us feel good inside. I definitely need it. Probably Siddhant too. He has a lot of work lately. So, help out my boy, young Sid. Next, this next Tuesday, the 15th, we'll have our IEEE research fair, which is going to be 5 to 7 p.m. It's going to be online, link to be announced. And if you're looking to get into research, if you're looking to, see what's up with working in a lab, you want to, get your hands wet with some more advanced projects, definitely come out to the research fair. There's going to be a lot of really cool and interesting ECE labs there, and it's going to be a great event.
And next some of them might use Verilog additionally. So
that is true. Next, we have our movie night. Next Thursday, a week from today, 8 p.m., Tesla Room in E4. I don't know if the movie has been announced yet. So, if someone knows, please say it in the chat. But otherwise, it'll be like a crazy surprise, I'm sure. It'll be a really good movie. It's Encanto. Wow. I love Disney. Next, Friday is going to be our Frisbee night, 7 p.m. at Drake Stadium. IEEE has always had a very, tight and warm connection with UCLA Frisbee. So, this is just our chance to, partake in our traditions and, go back to our roots. And, something that I forgot to put on the slides, but is equally important, this Saturday is our first GB takeover. It's at Saxon Grill, and we will be taste testing various bubble tea from all around Westwood. So if you're ever, people ask you, yo, what's your favorite bubble tea in Westwood? And you don't really know, this is your chance to decide once and for all. Hosted by the GB Roasted Not Fried, headed by our very own President Caleb, which I'm sure you guys all saw a picture of before coming today. Okay, and finally, next workshop is going to be our FPGA workshop. Again, there's a lot of hype about this. Super secret, special guests. They have been putting in a lot of work for this. And, this workshop is going to directly tie into our next workshop. So come out to that one as well. All right, let's get started then. That's all of our announcements. So first, if you have, this is our Verilog workshop, but if you've never, if you've never taken a Verilog class before, or you don't know about Verilog before, you might be wondering, why Verilog? What's so special about Verilog? And why, why are we hyping it up so much? Well, the reason is because usually when you are making circuits, you have the breadboard or the perf board in front of you, and you're trying to poke stuff into the breadboard. You're trying to solder stuff, and then the breadboard is broken, or you have a cold joint when you solder and it doesn't work, and you are trying to prototype your circuit and it doesn't work, and it takes a long time to change the circuit. And God forbid, you print a PCB, you order it all the way from China, and it gets to you and you find out it doesn't work. And so prototyping takes a long time and it's really costly. So we would like to find a kind of faster way to simulate these circuits before we put them into production in real life. And that's where Verilog comes in. It's what we call a hardware description language. There are several out there, but Verilog is probably the most relevant one. And they allow you to synthesize a variety of circuits whenever you want. Basically, all you have to do is change a couple lines of code and you can get a completely new circuit. And after you're sure your prototype works, that's when you can make a permanent version, you can solder it, order PCB, whenever you want. Some other perks is, again, it's the industry standard, lots of opportunities for jobs and research. Again, come out to the research fair with your new Verilog skills next week. It's a great resume skill. So, recruiters love to see it on your resume. If you like coding, but you also like circuits, this is, a good compromise between them. It also helps you pass ECE M16, which, I've heard a lot of people have trouble on. So, you're welcome. So before we get started with Verilog, we have to kind of talk a little bit about binary. I'm sure you can all count to 2, and you all know a little bit about binary, so I'm going to go quick on this part. Humans, usually we count in base 10 because we have 10 fingers. So we count from 0 to 9, and at 10 we go to the next place. So we have, 1st place, 10th place, 100th place. Unfortunately, computers don't have fingers yet, but food for thought, Tyler. If they did, how many fingers would they have? I mean, I called out Tyler because he's eating right now, but it's for everyone to think about. Anyway, binary is base 2, and I'm sure, just a quick refresher, if you want to convert from base 2 to base 10, you start from the right and you multiply each digit by 2 to raise to the power of the digit place, starting from 0. So for example, this example on the right, we're starting from the right. So 1 times 2 to the 0, that's going to be 1. 0 times 2 to the 1 is 0. 0 times 2 to the 2, 0. 1 times 2 to the 3, 1 times 2 to the 4. You add them all together, and that is 25. And so this binary number is 25 in base 10. Just a bit of vocabulary real quick. In binary, we say that 1 digit is equal to 1 bit, and we say 8 digits are equal to 1 byte. But next, with our binary, of course, we can do addition and subtraction. It's a real shocker, I'm sure, and it works basically the same as you would in base 10. You just start from the right and just add them together, and if you have a carry, which is a 2, that becomes 1 in the next column, and yeah, you just add it through. So for this first addition example, we have 1010 plus 0100, and again, you start from the right, so 0 plus 0 equals 0. 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 0 equals 1. So you get the answer 1110. And after we have this addition and subtraction, we go back to this problem. What if computers had 16 fingers? Well, then we would need a base 16 system, because we're counting to 16, but we don't have 16 fingers on our hands usually, I think. Well, okay, and that's also like a problem because we can't count up to 16. So what do? We use letters. So instead of counting from 0 to 10, we count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So A will be 10, B is 11, all the way to F, which is 15. And you'll carry at 16 instead of 10. So if you've taken CS33, you might recognize this notation, often used in computer addresses and such. And you generally denote hexadecimal numbers with a 0x in front of them. For example, 0x, 1a, 3b. So each hex digit represents 4 binary bits, because 4 binary bits is 2 to the 4th, that's 16. That's exactly our base in hexadecimal. And 2 hex digits is a byte. And we have a couple of examples here on the right, as well as counting guide for you. And yeah, so now that we know about hexadecimals, let's talk a little bit about digital logic.
So basically, we've now covered how computers can count, and basically we can convert numbers that we understand, right, decimal to binary and hex. So the next question we want to answer is, what can computers actually do with all this binary or hex, right? Because without being able to do anything with the data, a computer is basically useless. It doesn't do anything for us. So next slide, please. Okay, so digital logic is basically how computers think. If you've done coding before, you might have like variables where you name them, random things, but the computer doesn't actually care what it's called, or like what you're actually storing on it, because in the end, the computer only knows binary, right? So anything you're storing or doing operations with in a programming language, at the computer level, we have basically binary operations, just zeros and ones. So the computer then takes your variable and stores it as a sequence of a bunch of bits, which is basically like either high or low voltage. And then when we write our circuits, we can basically not actually pay attention to what all the individual bits are doing, because we're able to abstract some of that away. So before we get into some of the more fancy things you can do in Verilog, let's just talk about some of the basic bitwise operations. So if you look on the right, there's some Verilog syntax. So if we have the AND operator, it's the ampersand. And if you want to do a bitwise AND, you would have to have like a bit on the left, and then the AND in the middle, and then the bit on the right. And then your output is going to be those two bits ANDed together. And for those of you that are unfamiliar, the AND gate does exactly what you think it does. So if both of them are ones, then the output will be one. But if only one of them is ones or neither of them is ones, then the output will be zero. We're basically having the output be one only if both inputs, input one and input two, are going to be one. So that's one of the more basic operators. We also have Boolean inversions. So like the not will basically just flip a 0 to a 1. XOR is exclusive OR. We'll get to that later. We could also shift bits to the left and to the right if we want to manipulate our bits. And then Boolean operators is what you'd be familiar with if you've used a programming language like C. So that would be like the true and false. The difference between the bitwise and Boolean is the Boolean is basically either 0 or 1 for the whole string of bits, and the bitwise does the operation on every single one. Yeah, can you give an example of a shift? Okay, so say I have 4 bits of binary, and I have it, let's see, if I have 0, 0, 0, 1, that's our 4 bits of binary. And if I did a left shift by 1, I would basically shift all the bits left. So that means the bit that was already the farthest left just gets thrown away, and then everything else moves 1 over. So as David put in the chat, that's what a bit shift operator would do. Okay, next slide, please. Okay, so here are some examples of the simple ones from the previous slide and what actually ends up happening. So as I mentioned, and the output's going to be 1 if both the inputs are 1, or if either of the inputs are 1, then the output will be 1. And then the NOT gate is the simplest. It just flips whatever the input is, each bit of it. So on the right, if we have multiple bits, like I mentioned, we could have 4 bits. If you did a NOT on the 4 bits, it would actually go bit by bit and it would flip all of them. So that's why they're called bitwise operators. Okay, so now that you know the syntax to actually code this in Verilog, it's important to keep in mind what's actually happening behind the scene. So Verilog lets us model physical circuits, and these logic gates, the NOT, AND, NAND, OR, and there's a few other, are basically physical components that could actually go into a circuit that are made from transistors. And then when you actually design a circuit like a processor or something like that, you're just going to have a bunch of them on one large chip. And instead of actually worrying about the bit level, we can use something like Verilog to only describe the higher level or what the circuit's doing, and then let the compiler handle some of the lower end stuff. So that's basically what we're doing here. We're trying to convert our ideas into these tiny little transistor-based components without actually doing each component by hand. Does that make sense? Yes. Okay, so now that we talked about some of the basic gates that, yeah, there's a sign-in link, that have to do with just a single bit, like the AND and OR, you might be wondering how computers do something like math. So there's actually patterns. If you look at like adders, with if you're adding like 2 1-bit numbers, you have a sum and a carryout. And basically what that is an XOR gate and an AND gate. So the sum is an XOR gate because if you're adding 2 bits, the sum is going to be odd if both of them, or if one of them is 1. And then if both of them are 1, then you're going to have to carry over because the computer only has 1 finger. And so the sum will be 0. And then the AND gate, we only have a carry if both of them are 1 because the computer can't store both of them on 1 finger. So that's basically a half adder circuit. It's 2 of the smaller gates. And this is just an example of one of the many larger components you can build with gates. So on the left, we have an encoder, which can convert a 4-bit 1-hot input into a 2-bit binary number. And on the right is something called a multiplexer, which basically is, if you're familiar with coding, is like an if statement. You could select different options. And so this is what it actually looks like at the bit level. Okay, so everything we've described so far, you can sort of think of it as the output changing immediately. So whatever the input is, the output is just based on that. But there's cases where you want to be able to have some sort of memory, or you want to be able to do something based on the past inputs, or actually store the values. And that's where registers come in. So a register is a memory element, and we're not going to describe the internals of it, but here's the schematic. And register will basically let you store a value and update it based on a certain condition instead of always assigning the output based on the inputs. Does that definition of a register sort of make sense to everyone compared to just having gates? Yes, thumbs up, thumbs down. Can go slower. It's an option. Thumbs up, cool. All right.
Okay, so now that we've gone through the basics of digital logic, and everyone gave a thumbs up, so I'm really happy. We can go into some of the details about Verilog. Today we will be using an online Verilog simulator, which is called EDA Playground. So everyone go to EDAPlayground.com right now, because we're going to be coding there momentarily. And there we can write our system Verilog code. We can simulate our code and see some cool waveforms. And all you need to do is make an account and also go to this Google Drive link and download our skeleton.
I would recommend you just sign in with Google. It's going to be the fastest one. Just takes a couple clicks. So whatever account you have, you don't need to use your UCLA one if you don't want to either.
Also, oh, I forgot to make the link. All right, Siddhant, put the link in the chat. Dang.
So yeah, that's the link at the bottom of the slide.
Same wavelength.
Yep.
Telepathic communication here. What's going on? Okay, anyway, everyone go there. There's 3 files at that link. Please download all of them. And we'll be using them for our demo momentarily. Next. Again, Verilog is a hardware description language, and basically that's a fancy way of saying it's not like C++ or Python or the kind of traditional programming languages that you've all used. And so it's a bit difficult to look up answers on Google just because it's so old, and the main users of this language are like 50-year-old like boomers. But you gotta live with it. It's part of the suffering is part of the beauty of Verilog. Anyway, getting started, there's 2 main parts to a Verilog design. The first is the modules, and the second is the test bench. The modules are your actual kind of code that you write out what you want your circuit to do, and your test bench is the code that literally tests your modules for you. And these are done in 2 different files, and we're going to walk through kind of what goes into both of these files. So first, I'm going to talk through everything we're going to have to do, and Siddhant is going to walk through everyone. He's going to share his screen and walk through writing it alongside everyone. So first, you write your modules. They're like functions in traditional languages. You first declare it with the keyword module, and you write the name of whatever you want the module to be. You need a semicolon. This causes a lot of people a lot of problems when they leave at the semicolon. Silent killer. And the parameters, they don't need types. You just need to name them. And each parameter will be set as an input or an output. So here we have them clearly labeled as in or out, and you need to end the module with the keyword end module. So after you have this kind of function declaration going on, you need to define your nets. So again, nets are kind of like variables. Physically, they're literal wires that connect in and out of your function, your module. And in our modules, you define them as either input or output. And they can also be modified with the reg keyword, which stands for register. We're going to go a little into that later. And inside your modules, you can just give values to regular wires using the word assign. So here you can see on the right, we've declared our input and output in and output out. And we have just kind of a bit of code going on in each module. Assign out equals in XOR 1, or always begin out equals the inverse of in. We're going to explain what happens in always blocks a little later, but just so you know for now. And real quick, just before we start the demo, some special Verilog syntax that we should all know going into what we're going to do. First, this 8B00100010, this 8B, the 8 denotes that it's an 8-bit number, and B denotes the base. So B stands for binary, again, base 2, like we just talked about, with that exact value. Next up, when you use the curly braces, it concatenates everything inside those braces. So here we have 0, 1, and 1, 0. With the curly braces, it will concatenate them into 0, 1, 1, 0. If you have a number in front of the curly braces, it'll make copies. So here, it'll copy the 0, 1 3 times. And next, for loops, your old friend from C++ is back. You write them basically like the exact same way as C++. So that's a nice thing about Verilog. See, it's not so different. Yeah, so that was a lot of text. Let's try walking through everything together. So everyone, Siddhant is going to take it away here, and he's going to walk us through kind of from start to finish, just uploading the files onto EDA Playground and just writing everything step by step.
Okay, so let's see. 1 second, let me find the right. Okay. Was everyone able to use the link and get to this right here, the 3 files? Cool. Okay, so move this annoying little zoom bar. So if we go to EDA Playground, you're going to have this sort of interface right here. It's going to give you 2 blank consoles. And as David mentioned earlier, the one on the left is going to be for the test bench, and the one on the right is going to be for the design. So right now, let's just start with the design. You can upload it if you want, but since the file's already there, I think it's easier to just copy paste. Okay, so this is like a code skeleton. And before we continue, let me briefly explain what our demo is going to be. So you might have noticed there's a input txt file. So this is a bunch of hex, as David mentioned. And so the idea is we're going to take this hex, which is a bunch of encoded messages, and then we have to do some combinational logic in Verilog and try to see if we can figure out what was originally in the messages. So once everyone has their code copy pasted on the right, I'm just going to format this in a little nicer way. Okay, so we're going to start right here on line 10. So as David mentioned, we're going to be writing the code for our first module. And so our first instruction is to declare our module called stage 1. So does anyone remember the keyword that we have to use? Just feel free to unmute and yell it out. How do we tell Verilog we're starting a module? There's some hints throughout the page.
Module.
Module, perfect. So we just say module and then the name of it, which stage 1. And then remember to have the end module, which will be right here. Okay, So this is our code that we're working with for now. Okay, so what goes in these parentheses? Jeopardy music.
Inputs and outputs.
Inputs and outputs. Okay, so in this case, we can just call them in and out, separate it with a comma. Okay, so we've declared our ports, or we have our ports onto the module, and now we need to specify to Verilog what they actually do. So in is our input, and then out is our output. Okay, so our first instruction is to invert all the input bits. So let's say we want to assign the output wire to, does anyone remember what we have to do to invert bits? It was from some slides ago where we talked about the syntax of individual gates. Yeah, there you go. So Caden put the symbol in the chat. So it's this little symbol right here. And then you can just do that. Tilde. Thank you. Okay, so that inputs all the or inverts all the bits of the input. Now we have a problem here, and that is that in and out are just 1-bit wires. And so this doesn't really help us decode our message because our encoded message is it's very large. So as you can see here, we have some fancy array indexing. Basically what this means is our wire is going to have bits 191 through 0. So just like in some programming languages where we start with 0, that's typical in Verilog. So basically what this is saying is that we want 192 bits. So if I want to tell Verilog that my module is going to be dealing with 192 bits, I'm just going to copy that syntax. So the bit all the way on the left is called 191, and then the one all the way on the right is called 0. And then the colon in between just tells Verilog to fill in the blanks. It's like ... Okay. And then the same thing for our out. Okay, so now our output is basically taking the 192 bits of input, going through, and then flipping all the bits and making them, assigning that to the output of this module. So let's see what the next stage is. Then we need to XOR each byte with the key, and we have 8 bits here. Okay, so we can replicate the key to 24 bytes. So this is 1 byte. Does anyone know how we can basically copy this 1 byte 24 times without actually copy pasting it 24 times? There's a fancy little thing that was on one of the slides. Okay, yeah, perfect. So you have Pram has a 24 and then the curly braces. So first of all, the XOR symbol is this little caret. And then what we're gonna do is we want 24 times this right here, this 8-bit value. Okay, and then this is basically gonna make it so that our input and this thing are the same size. So we can go bit by bit and XOR each of the individual bits. Okay. So it says next we need to swap the first and second halves of the result. And this is the module's output. Okay, so we already have like 3 things going on in this line, and it's getting kind of complicated. So what we can do is we can basically declare the equivalent of a temporary variable in a programming language. So we can just call that a wire. And this is not a port into the module. This is just a wire that is within the module that we could do stuff with. So we want it to be the same size. And then we'll just call it temp. Okay, and then instead of assigning the output, we'll assign temp right here. Okay, so we now need to swap the first and second halves of the result, and this is the module's output. Okay, so we are assigning the output. Okay, oof. How are we going to swap the first and second halves of the result? Any ideas? So it has to do with this little funky array indexing that we mentioned earlier. Any ideas? We can do this in one line. Store it in another wire, bit shift. Okay. Bit shift is a valid way, but there's an easier way. And that is if I wanted something, if I just wanted half of this, if I wanted half of the input, I could say something like this. I want temp. And I want them to give me the First, what's half of 192? I'm bad at math. 96? That sound right? I think it's 96. So
It's 96.
it's 96. Okay. So if I do this, I'm basically taking bits 191 through 96, which is the left half of the temporary variable, and I'm assigning it to output. But the problem is the output is 192 bits and we only have half of it. So we need to get the other half, which is just going to be 95 through 0. Okay. How can we put these two together in a different order? So we have the first half and we have the second half, but we need to flip the order in the output. Okay. I'm not sure if this was on an earlier slide, but we can add zeros and add. Okay, so Tyler's got it. So you can concatenate. Yeah, Caden also's got it right. You can concatenate with a comma and the curly braces. So you could do something like this and then put a comma there. Problem is that we need to flip the order. There we go. Okay. So does this make sense to everyone? We basically took the first half and we put it at the end, and we took the second half and we put it at the beginning. And then the curly braces and the comma just means that we want to combine those two together into one long string of bits.
Okay, everyone, real quick.
Oh,
There's a
yep.
small error.
Small typo. Thank you.
All right, dang.
Okay. And then we have an end module. And then we've done our stage 1 module. So is everyone following along? Any questions on this first module? Could be about the syntax or like whatever is going on, or the operations that we're doing. If not, we can move on to the next step.
Oh, real quick, are people following along in EDA Playground?
Yeah. Let's see.
React if yes. Okay, that's cool. All right, let's keep going.
Okay. I think you should take over the screen share, right? We
nah,
should
you
have
just
more
keep
slides.
going.
Okay,
You
keep
just keep
going.
going.
All right.
You got it. I
Cool.
believe in you.
Okay. So stage 2 is going to be the next module here. And we've already declared the module. We just have to basically finish it. We're given a skeleton. Okay. So the first step is to declare the port mode. Someone tell me what I should be typing here for the in and out. Should be the same as the module before it. Okay, Jonathan's got it. So we want to declare a in and our output out. Okay, and then we already declared a temporary register just like we did before. And then I'll cover why it's a register in just a second. It's not a wire like the previous one. Okay, and then you'll notice there's an integer I here. David mentioned that the syntax for loops is similar to in C++, right? But in Verilog, the compiler likes it a lot if you just tell compiler that I is an integer at the beginning. You shouldn't do it within the loop, or it'll get mad at you. So we just did it right here. Okay, so here's our tasks for this stage 2. First, we want to use a for loop and flip the order of all the bits. So that means if I had bits that went if I had 4 bits that went 1 0 1 0, and I flipped them in order, we would want to go backwards. So we want our output to be 0 1 0 1, and we can do that with a for loop. Okay, so let's start with this for loop. Does anyone have any idea what we should be going to if we start at 0? If we want to flip all the bits, what are we counting up to in our for loop?
Oh wow, we got some CS majors here.
Yeah, you could do
Got it.
96 if you're more big brain than I am. But I'm not big brain, so I just do 192. We do each bit one at a time. Okay, so how can we flip the order of all the bits? So let's see, we're gonna assign temp, and we're gonna make it equal to, okay, so if we start with 0, I is 0, and we're talking about the far right bit of temp, we want the far left bit of the input, which is what for 0? So what should actually go here? Just if I is 0, we don't have to get into the mathy stuff yet. 191. Okay, perfect. So it turns out that that's basically, we're just starting with 191, and then we're just going to subtract I. So every time we move one bit on the temporary to the left, we move one bit right on the input, just so we're able to flip them and mirror basically all of our bits. Okay, oh, oops, this should be in. Okay, and then real quick, I'll explain some of the differences here. So you'll notice we have an always at star begin here. We're not going to get into always blocks necessarily, but just know that basically what we're telling the compiler here is always just basically continuously do this thing. So we just want to continuously flip all the bits of the input into the output, and we're not going to change the input like during this, so it doesn't really matter. It's just a syntax thing. We can't use for loops with wires. It just doesn't work. We have to put it in an always at star begin. And I'm sorry, it's confusing. Okay. Any questions on the for loop? We have a typo after line 32. Oh, oops. Thank you. You guys are human compilers. This is what we like to see. Questions for loop before we move on to the last task here? Okay, cool. So now our last task is to assign the output to the sum of our intermediate, so our temporary variable, and this kind of high number right here. So just like any programming language, we don't have to do bitwise operations in Verilog. We can also just flat out add things. So in this case, since the output out is just a wire, we're going to use assign. We're just going to assign the output to temp plus the number. Okay, but you should be careful because our output is like a kind of a weird amount of bits, right? It's not just like an integer. We have 192 bits. So it's best if we tell Verilog we want 192 bits. And as David mentioned on one of the previous slides, the syntax goes the number of bits, then you have this apostrophe, and you would put a B if you wanted it to be in binary. But we're not giving our number in binary, we're giving it in decimal. So we're just going to change this to a D, and it just works. Okay, any questions on addition in Verilog right here? No? Okay, so now we have a bunch of code that we copy pasted and it looks kind of ugly. So let's clean it up just because we believe in good coding practice and readable code. So I'm just going to indent things. Oops, I'm not. Okay. Make it look real nice when everything starts at the same horizontal place. Okay, so when we indent our code, it's a lot easier to debug. For example, we know the always begin. The end for the begin is right here because it's all aligned. This will make our lives easier in the future. Okay, does everyone follow what we did in the stage 2 module?
There's a request to go back and explain the flipping loop again.
Okay, so the flipping loop. Basically, just type here. If we had our input was, just ignore whatever's happening. So we have like some random string of bits. How many is this? It's like 5, 6, 7, 8, 9, 10, 11. We'll make it 12. Okay. So if we wanted to flip the order of all the bits, basically what we want is we want to start from here, and we're just gonna copy paste it in opposite order. So this would be the 0th bit of the input, but it's gonna be the 12 or the 11 bit of the output. So it would go right here. And then the bit 1 of the input would be the 11 minus 1, 10 bit of the output. And then so on. So this one would be a 0. Then we have a 1. And we have a 0, 1, 0, 1, 1, 1, 0, 1. Does that help explain a little bit what we're doing with I? Okay, cool. What are we accomplishing by setting temp to the same thing over and over? Do you mean are you asking about the always begin? Why? Okay, cool. So basically, always begin is something that you would use for sequential logic, or something that you would have to do with memory or timing that we kind of mentioned earlier when we were talking about registers. But you can also use it for combinational logic. And combinational logic is just basically what we've been doing here, assign with some bitwise operators. If you want to use it with combinational logic, you're just going to put a star in here, and basically, you're basically telling the compiler that the output always should just change whenever the inputs change. So it's not really doing this over and over again. It's just saying that anytime the input changes, we should update everything in this manner, with whatever is inside the always begin. Okay, and we're using an always begin because the for loop needs to be inside an always block. Okay. Any other questions? Is everyone caught up or following along? We get some reacts. Cool. And then if you notice any other syntax errors here, please let me know. I'm not a human compiler, but you guys are. All right, David, should we go back to the slides then?
All right, yeah, let's do that. All right, so, we've kind of written out our modules. Oh, maybe you should do the continuation too at the top.
Oh, okay, sure.
Yeah, let's do that real quick. Yeah.
Okay. Let's bring that back 1 second. Okay, so David's basically mentioning that we made a bunch of modules, but we didn't really talk about how to connect them. So let's say we have one big module that's decode. That's going to be the large module, and we could do littler things inside of it. And we have our decode has its own input and output, right? That's the encoded text that we're going to be reading. That's garbage, and we can't figure out what it has. And then our output is going to be our unscrambled readable text. And then we also have this wire that's going to be sort of like the temporary variable that we talked about in stage 1 and 2. And the reason we need this is because we have 2 different modules, but we need to connect the 2, right? We need to take the output from stage 1 and put it into the input of stage 2 so that we can continuously have the correct output of our module. So here's the syntax for instantiating a module right here. Basically, we tell Verilog what module we want to create. That's basically the name of the module, stage 1. And then UUT is just unit under task 1. This can be whatever you want. I could change the name of this to David Cow, and it'll work just fine. The idea is if you want to have multiple stage 1s, you should name them something unique so that you can debug easier and you can see what's going on. Okay. And then you'll notice in parentheses, we got sort of a weird thing going on. .in means the port in is going to be connected to whatever's in the parentheses. And then .out would correspond to the out port of module here. So basically what we're telling Verilog is to the in of stage 1, which is this port we just created, I want to connect encoded text. And then to the out of stage 1, we want to connect stage 1 out. And so basically the input to decode, we're just putting it into stage 1. And then whatever we get out from stage 1, that's going to go into stage 1 out. That's going to be our temporary variable. We just completed stage 2. So we need to add an instantiation for stage 2. So if someone wants to help me out and copy paste some code into the chat for me to just copy paste in here, that would be excellent. Let's see if you guys followed along with the syntax.
Guys, if you get this right, there'll be a special prize straight from the workshop's budget.
Okay, close prime, but we're doing stage 2. Almost. Okay, so Caden, bingo. So we have stage 2. We can have whatever name we want. We could call it UUT2. And then in the input, we want to feed in the output of stage 1. That's our little temporary wire. And then in the output, we just want to put decoded text because we only have 2 stages. We can just connect this directly to the output. Okay, and so now we've created 2 modules and we've connected them together inside of a bigger 3rd module. This is big. And this is mostly done. And after we go back to the presentation, we'll talk about how to test to make sure we did everything correct and fix any errors.
Okay, everyone clear about how we just connected our 2 modules just now? Cool. You know, we had like a big module, and inside the big module, we had 2 little modules. Yes. Okay. So after we've, written our modules and we, decided what we want our circuits to do, and we coded it all out, what do? We write our test bench. Honestly, writing the test bench is very tedious and more annoying than actually writing the code. But, you have to do it. And so at the start, we said that, the modules and the test bench are 2 different things. But secretly, the test bench is also a module. As you can see on the right side, we have kind of an example test bench for you. Just like all modules, you create them with the module keyword, you end them with the end module keyword. And the one thing that's different here is there's no inputs to this module. It only has outputs. What you do instead is you define inputs to the modules that you're testing. And this will make sense on the next slide, which is right here. What we're going to do is we are going to instantiate an instance of our module. So here in this example, we have written a module that's named mux_4_1. That's a multiplexer. And we have called it UUT, unit under test, as Siddhant said. And what we did is we are using the inputs to that module. For example, we have our inputs in 1, in 2, and 3, and 4, as well as select. And we also have our out signal. So those are all called those are all like kind of created in the test bench. And so once we've instantiated our module that we're trying to test, what we do is we initialize some of our variables. So for example, in our mux, it has 4 inputs in 1 through 4. So to initialize these variables, we're going to create an initial begin block right there from line 10. And what we do is we just define whatever we want our starting variables, to be when we start out. And so here we just like picked whatever starting inputs, but if you want, you can test out your inputs systematically and try to test all possible cases. And after that, if your test bench works, you can try to test them and just run the test bench. But first, one thing about syntax, kind of Siddhant already kind of went over this in the code, but we should talk a little bit about always blocks. They're an important part of Verilog. And the thing about always blocks is that they are always active, hence the name always. They start at the beginning and they finish at the end of your program. And the one key thing that you should know about them, the one key takeaway is that if you're trying to change a register, you have to change them inside an always block. That's just just something you have to do with Verilog. And so there's several kind of shapes that an always block can take. For example, always begin on the top right. It's good for test benches. It just always goes, just constantly doing whatever's inside it. Always at, which is good for modules. After the at, you can put kind of a signal. For example, on the bottom example, we have always at clock begin. And this is basically shorthand for saying, whenever the clock signal changes, do this. Or if you don't want to change at a specific signal, you just want to change whenever anything happens, you can do always at star, which is at the bottom there. And if we kind of look at the top right example again, we have always begin something equals not something, and then we have end. So if this was in our test bench and we're trying to test one of our inputs with this something, can anyone kind of think of a potential problem that might arise because of this? Because of this specific syntax. Okay, while you all think, would the always at clock begin change on each edge of the clock or only when it's high? That's a great question. I think it's mentioned a little later, but always at clock will change it whenever the variable changes. So, so whenever you have a change to the variable, for in this case, the clock. Miriam, does it never end? That's close. It's something about the timing of this block. Remember, when we're writing our code, we should keep in mind that we're writing real life circuits, with electricity and electrons that they run around and stuff, and they flow like water, or whatever metaphor you use in school. It would burn out because too fast. Okay, Prem, you've kind of got it. The key is that this always begin statement is constantly going. So this something variable is always inverting. It just keeps going. There's no time to respond. There's no time for the system to respond. So actually, this is not that helpful when we're trying to test something that relies on this something signal. So what we do instead is we use the delay operator, which is the #, number sign, hashtag operator, whatever you want. And this delays it by however many ticks you want. In the top right, we have it delayed by 10 ticks. So this # 10 will delay by 10 every time the always block loops around. It doesn't need a semicolon or anything. And this way we can kind of prevent this something flag from just constantly, instantly flipping back and forth and not giving the system time to respond. And this way, in that 10-second delay, we can see what the system would do in response to our inversion. And after this, we can define our initial begin, and we initialize it as something equals 0. And we can also define a runtime using the same syntax, the $ 40, and we end with $ finish. So, quick question, given these two code snippets, can anyone tell me how many times will the something signal invert? All right, Caden, got it again, 4. That's correct. In the bottom statement, the initial begin, you define something equals 0, and you wait for 40 ticks, and then you finish. But at the same time, the always block is also running, and that flips every 10 seconds, 10 ticks. So it'll flip 4 times, and then the finish command will be called. So, it'll flip 4 times. Does that make sense, everyone? Dang. Also good call out about the redstone blocks. Digital logic, is a thing in Minecraft too. If you want to be a computer architect, Minecraft is not the worst place you could start. Anyway, now that we kind of talked through what happens in the test bench, let's kind of run through it in real time.
The test bench time. Okay.
Yes, test bench time.
Let's see if I can find the right. Go to EDA Playground. Okay, so the other file, or one of the other files inside this folder that I've shared, is the test bench file, which is right here. We're gonna do the same thing and just copy paste it because it's easier than downloading and uploading. And then of course that means the formatting is gonna look ugly. So just bear with me 1 second while I make this a little more readable. Okay, so you don't actually have to write any code for this test bench. It's complete, but I'm just going to walk you through some of the things that David mentioned in the last couple slides and where they exist here. So remember that the point of the test bench is to test the module that we just wrote, but it's also basically a Verilog module itself. So it's got the same keywords, module and end module. And in theory, I should put this as an output and put it in here, but it doesn't really matter. If I wanted to show this under like waveforms and look at what the output looked like, I would want to declare it as a port. So I would put recovered here and then change this to an output. Okay, it's not happy with me. Okay. So we got registers and wires and outputs, just like we mentioned previously. And then don't worry about this. This is just some syntax that you can use to read files. Test benches are very powerful, and basically you would use this instead of doing something on hardware. So if you wanted to use an FPGA, you could just upload your code onto the FPGA, and you could use like the switches and the displays and basically see if it works that way. But we're not using an FPGA today. If you want to use an FPGA, you should come to the FPGA workshop in 2 weeks. But for now, we're just going to be using display statements in here to see whether our code works or not. So in the initial begin, all of this just runs one time from start to finish. We basically are just opening a file, and then we're going to run for like 65 nanoseconds. And then we're going to stop. Stop does basically the same thing as finish. I just am used to using stop. And then as David mentioned, we can basically make our own little clock here just by inverting the thing every 1 nanosecond. If you were using an FPGA, the FPGA has its own clock, but we don't have one. So we're just going to do this. Okay. And then as David mentioned, we can have a block of code and an always block that basically runs every time the clock goes high, or pause edge clock. So basically what this test bench is doing is we're going to open an input file. We're going to start constantly driving a clock. And then every time the clock signal goes to 1, we're going to grab a line from the input file, and we're going to put it into message in, and then we're going to do this display statement. So message in is connected to our decode module that we just made, and recovered is going to be the output. So just like David mentioned for instantiating modules, it's basically the same thing we did for decode. We just put the name of the module. You can call it whatever you want, and then the ports. Okay, and then the last thing we need is the actual text file. So this one you do need to download. I'm just going to download it here. We have a question in the chat. Yeah. Okay, so say I want to upload. Will this work? Perfect. Okay, so here's the text file. You can just drag it over here. And then I'm going to want to save it, but basically for EDA Playground, you need to pick a valid tool or simulator. And the simulator is basically what's going to show us our display and basically see if our Verilog code is correct and can synthesize the way we want it to. So for the purposes of this, we're just going to use Icarus Verilog. Any of these three should work fine. Just use 0.9.7. You don't need to worry about the compile options or anything. So you could just select Icarus Verilog and then you should be able to save. Okay, that scared me for a second. Okay, and then if I hit the run, it's going to read line by line from the text file. It's going to feed the line into your decode. Your decode will feed it into your stage 1. You're going to get a stage 1 output, put it into stage 2, and then your decode is going to output the decoded text, and your test bench, we're going to display it. That's how we check to see if our code is correct. And we have done so here. Also, if you're at all curious, like if I took this hex and I tried to figure out what characters it was without decoding it, just out of curiosity, I could just change this to /s, which is a string. This is what it would actually look like, by the way. You can see the input and output. So this UTF-8, it's basically a way to convert binary into characters, but not all binary maps to like characters we can see. So it looks kind of confusing and troll, which is why we were just looking at it in hex. Okay, any questions? I see there's some stuff going on in chat. Okay, just faces, cool. And then we have our hex here. So any questions? Does everyone's code compile and give you the output we want, or is it we have questions? Oh, Prime?
Okay, I have a question. So like, is Verilog only used for prototyping and testing out circuits, or can you actually use it commercially? Like, can you send it to some sort of manufacturer that makes the circuit you're trying to make?
Yeah, so there's kind of a few different applications. So one of them is if you want to use an FPGA, which again we'll cover in a couple of weeks. You can use Verilog to program the FPGA, and basically you have these wires, right? And wires, inputs and outputs, and those wires can just be connected to some of the things on the FPGA, like the switches or the buttons. So you can do stuff based on when you press the button, you want to like show a number or something like that. But also, if you wanted to design a application-specific integrated circuit or an ASIC, then you could also do that in Verilog, and you want to check to make sure it works. And then I guess Caleb probably has a little more information about this if you would like to chime in.
So all the chips that are in like your phones, for example, like Apple's like M1 chip, these are all designed in Verilog, system Verilog actually. And they work with TSMC and their tools to convert the circuit that's actually designed into the actual chip itself. So the answer is yes, like Verilog is used for FPGAs, it's used to design silicon. It's used for a lot of stuff, yeah.
Cool, thank you.
Okay, any questions about the test bench or the output, or I guess anything before we go back to slides? All right, excellent. So I will stop screen sharing.
All right. We just did the test bench, super important, but before we wrap up, I want to cover some last topics about Verilog that you all should know about before going away. The first thing is the clock. We've kind of just talked about the clock. We use it in our test bench, but I think it would be good to kind of talk about what a clock really is. Basically, a clock is a signal that switches from 0 to 1 to 0 at regular intervals. For example, it might switch 100,000 times per second, or you could define it as a frequency, for like 1 megahertz or something. And some parts of the system like the circuit system, they depend on timing. For example, we talked about registers. They are clocked components, which means that they depend on the clock to operate properly. And the important thing is, I think someone asked a question about this earlier. Each clock cycle has a positive edge and a negative edge. So if you look at this diagram on the bottom, you can see one clock cycle is like one complete period. It goes down and then up. And the positive edge is when it is going from 0 to 1. It's like it's going up. And the negative edge is when it's going from 1 to 0. So it's going down, negative. And we should also talk a little bit about, with the clock, we should talk about sequential logic as well. There is, in digital logic, there's something called, there's a difference between combinational logic and sequential logic. So combinational logic is what we did just now. It only depends on the inputs, and it doesn't depend, you don't really need a clock for it whatsoever. For example, if we made an adder like it was on the slides before, or we made kind of like a decoding function like we made just now. Once we know the inputs, we definitely know what the outputs are going to be. It's going to be just the XOR or add whatever of the or reverse of the input. But the thing is, in real life, some circuits are sequential. It means that time matters too, and the time you look at the circuit, you might get a different output. So real life example, this is not a circuit. If you're driving somewhere and you're deciding where to turn, that is kind of a sequential type of thing, because where you are on your path will kind of, the turn you're going to take kind of depends on where you are in your path. If you're kind of deciding on the spot, oh, should I turn left or right? You need to, you need to determine like where you are, how far you are, how many turns you've taken, things like that. But in real circuits, in real circuits, the main important thing is that if you use registers and you're storing things in registers for later use, generally that will be an example of sequential logic. And if you want to see this in action, where the output depends on not only the current input, but kind of what happened before this, you should come to next time's workshop, because that's like a really good example of your output depending on your time as well as your inputs. Okay, if that didn't make sense, my bad. But important to know this distinction. And finally, one feature of EDA Playground that we did not cover is that you can see your waveforms, and the waveforms will show you what your module is doing. If you remember, each signal is either a 1 or a 0, and if you are trying to simulate your code before you make it permanent, you can simulate it and take a look at the waveforms, and the waveforms will basically tell you what exactly all your signals are doing, and you can look at the waveforms and it'll give you a visual description of what your system is doing. So if you're doing this in the future, it'll look like this. We didn't do it here because we kind of have our output displayed for us in our test bench in text. But if you're really doing this and you're trying to look at it bit by bit, we have, again, our multiplexer example. And you can see each signal, what it's doing over the course of the test. So you can see in 1, it's 1 for the entire time. In 2 and in 3, they're 0 for the entire time. And in 4, it's 1 for the entire time. And the output, you can see it's changing as the simulation goes on. So it first starts out at 1, and then it goes down to 0, and it stays at 0, and then it goes back up to 1. and you see at the bottom your select signal for what you were trying to pick as your output. And in this way, you can check your output and be like, oh, I wasn't expecting it to be 0 here. It was actually 1. And this is a good time for me to go back and trace through my code again and see what's going on. Yeah, if you're kind of working with Verilog in real life, definitely waveforms are your friend, and you should, definitely learn what they mean and what they're telling you, because then you'll ask someone for help and they'll be like, oh, let me look at your waves, and then you'll be back at square one. Okay. Any questions up to here? Okay, bang. Last slide. There's a lot of Verilog, and there's definitely a lot going on in this language that we definitely did not have time to cover today. But some quick things that some more advanced topics that we would get to if we could. Things like timing. So there's such thing as blocking assignment and non-blocking assignment. You can do different things with modules. You can have things in different bases, like base 2, base 16, base 8, whatever you want. There's such thing as multi-threading in Verilog as well, which is crazy. And when you actually try to synthesize these circuits onto an FPGA, there's also a few tiny details that sometimes need to be changed, but that's a problem for next time when we take our Verilog to the next level and we synthesize onto FPGAs and make circuits in real life with code. Wow.
All right. Just to reiterate or wrap way back to the beginning of the slides, because this was a dense workshop. I just want to remind you guys sort of the difference between Verilog and something like C++. So when you write C++, you're basically building a program that you want to run on a computer, and the computer looks at all of your code and then basically turns it into instructions and does what you want and puts it on your screen. So Verilog's not really a programming language because we're not building programs. We're actually trying to build a circuit. And so it's not really running on something. The modules are basically little mini circuits themselves. They have inputs and outputs and all these little transistor-based gates in between that we're just pretending to lay out by hand, but we're doing it through code on a screen. So that's the gist of what we covered today. It seems like it's very coding-ish when you're just doing test benches, which is why it's way more fun if you actually get to use an FPGA and play with the hardware. So hope you guys all join us in 2 weeks. We'll send more information out about that. Any questions? They don't have to be syntax related if you just have questions in general about Verilog. Yeah.
How does this make you feel? Everyone.
Oh, first of all, will you share the slides? Yes. I'm going to post the link to the slides in the chat, as well as the skeleton and the sample code, and then the recording will be up in the next day or two.
Super interesting. Wow. Thank you, Keaton. You answered that question before. I won't forget. I'll remember this forever. Is there a Verilog debugger?
You are the Verilog debugger. I'm kidding. The best thing you can do to debug Verilog is basically look at waveforms. We didn't do waveforms because just the purpose of our module is to take in binary and convert it into a string that we can read. So it didn't really make sense to display them on waveforms. But if you have larger designs, the best you can do is have waveforms because you can see them all side by side. And when you do logic, I want this wire to be the AND of these two wires. And then when you see them on the screen, you can figure out if it's actually ANDing them correctly or not. So that's basically the best way to debug your code. But to my knowledge, there isn't a special debugger for Verilog. Okay, so if you don't have any more questions, you should feel free to. Oh, how was your day? It was excellent, Ryder. Thank you for asking. What about you, David?
It was all right.
All right, yeah.
It was all right. Yeah.
Seeing all of you guys here today, so
Yeah.
engaged, made us happy.
Seeing all your lovely faces, it made me feel good inside.
Yes. We haven't seen some of you guys in like a whole quarter, so week 8, that'll be in person.
Yeah.
All right. So if you don't have any more questions, you can feel free to leave the Zoom meeting. We're not going to be covering additional content. If you have questions, feel free to stay.
Thank you, guys.
Look out for another really cool graphic incoming.